So we now know, provided our very strong assumptions are true, what the variance of the OLS estimator is. We know how to make the estimates more efficient by either increasing the sample size or increasing the variability in the explanatory variable. But we still have a problem, and that is that we don't know what this sigma squared u is. Sigma squared u is the variance of the error term. We never observed the true error term, and so we're going to need to estimate this. Now, the way that we can estimate this is going to look very similar to constructing an estimate of the variance of x. We're going to use an estimator based on the sum of squares of those fitted residuals. Now, there is a hidden minus u hat bar here, but remember when we constructed OLS, we constructed it such that the average of the u hats is equal to 0. So we can use this estimator as an estimator of the variance of u. Now you might say to me, hang on, why are we dividing by n minus 2? Well, this is a degrees of freedom adjustment. When we're constructing each observation of the u hat, we are using estimates beta 0 hat and beta 1 hat to construct that estimate. So by using those two estimates in the u hat, we're losing 2 degrees of freedom. So this n minus 2 is a degrees of freedom adjustment. Just like in s squared we divide by n minus 1, in this case we're dividing by n minus 2 because we're using two estimates in the construction of our estimate of the variance. So we can construct an estimator for the variance of the OLS estimator based on this sigma hat u squared, 1 over n minus 2 times by the sum of the u hat squareds, divided by the sum of the x minus x bar squareds. So let's summarize. Provided our assumptions are correct, the OLS estimator will be approximately normally distributed, centered on the expectation of beta 1 hat, which, if our assumptions are true, will be beta 1, and with variance equal to sigma squared u over the sum of the x minus x bar squareds. We're unlikely to know the true variance of the error terms. If we did know the true variance, then we could standardize our beta 1 hat by subtracting the expected value of beta 1 hat and dividing through by the square root of the variance. But in reality, we're going to need to estimate that variance. And it would follow a t-distribution with n minus k minus 1 degrees of freedom, where k is the number of explanatory variables. So when we've been estimating the relationship yi is equal to beta 0 plus beta 1 xi plus ui, we've got one explanatory variable. We're estimating two coefficients, so we'll have n minus 2 degrees of freedom.